In many labs, you're going to find that we're going to have an excess of one of the reactants. This example takes that into account. In this example, we are given data from a certain experiment. So in a certain experiment, 28 milliliters of 0.250 molar nitric acid and 53 milliliters of 0.320 molar potassium hydroxide are mixed. What is the concentration of H plus or H minus ions in excess after the reaction goes to completion? So we have a lot of different things in this problem that we have to take into account. Because there's a lot of information, I would recommend taking your pencil and underlining given information. So as we go through this, underline information in your problem as well. So we know that we have 28 milliliters, and we know that the nitric acid is 0.250 molar. So those two pieces of information go together. So I'm going to underline both in orange. And then we know that we have 53 milliliters and 0.320 molar potassium hydroxide. Those two values go together, so I underlined it in blue. Now what we have to do is we have to figure out first which ion is in excess, and then calculate the concentration. So the first thing we're going to have to do, because this is going to be a stoichiometry problem, we saw the word excess, so you know we're probably going to have to do stoichiometry. First thing, write an equation. Nitric acid, HNO3, right? Nitric, you ate something icky, so nitrate goes to nitric. HNO3, which is aqueous, think about why it's aqueous, plus potassium hydroxide, same thing, think about why that's aqueous, yields potassium nitrate plus water. Potassium nitrate is aqueous, look at your solubility rules, water is a liquid. So that is our molecular equation. That's our overall equation that shows the stoichiometry. Now, think about what the net ionic equation would be, and I want you to write that down in your notes right now. So pause the video, write down the net ionic equation. And then if you take a look, I wrote the given information down underneath the molecular equation. So I wrote down the volume and the molarity of nitric acid, the volume and the molarity of potassium hydroxide. Those two pieces of information are going to be key because volume and molarity allows us to find moles. Whenever we do stoichiometry, remember you have to find moles. Now in this case, because it's a limiting excess reactant problem, I set up a BCA table. I think BCA table is a little bit easier to visualize when you're working with limiting reactants, but you can definitely just do the stoichiometry if you prefer, like we discussed in Chapter 3. So what I did is I took my volume and I took my molarity, I found moles. Okay, so set up your molarity formula, calculate for moles, you multiply the two, but make sure milliliters is changed to liters. You get 0.007 moles of nitric acid. That's before the reaction starts, that's why it's in the B, right? B is before. Then do the same thing for potassium hydroxide, you get 0.01696 moles. So that's the amount that we have before. Notice before for both products, it's 0, you don't have any products to start out. Now we have an amount for both reactants. If you're given an amount for both reactants, you have to figure out which one's limiting. Now if you look at the molecular equation, it's balanced. What do you notice about the ratio? It's 1 to 1. So for every 1 mole of HNO3, you need 1 mole of potassium hydroxide to neutralize. Well, if you look at the amounts, you should have equal amounts. If it's a 1 to 1 ratio, your lower amount is going to be your limiting reactant. So what that means is if we look at this, for every 0.007 moles of nitric, you have that and more. So potassium hydroxide is excess, nitric is limiting. That means throughout the rest of the problem, we have to use nitric acid for all of our calculations. So if we take a look, we look through, let's work through this BCA table. So if you notice at the top, what I did is I went from the molecular to the net ionic equation. Net ionic is what we want to focus on. We don't care about the overall molecular. We want to forget the spectator ions. So check your net ionic. You should have this. So H plus is our limiting, right? H plus comes right from the nitric acid. The hydroxide is our excess. That comes right from the potassium hydroxide. If H plus is our limiting, we use that up completely. So we use up all 0.007 moles. So after the reaction, we have none left. Well, if this is a 1 to 1 ratio, that means if we use up 0.007 moles of H plus, we use up 0.007 moles of hydroxide. Can't use up any more because you don't have any more H plus to use. So after then, if you subtract the two, you get 0.00996 moles of hydroxide. So hydroxide is your excess. That's the first important thing to note. Okay, we know now that hydroxide is going to be our ion that's in excess. Now we just have to work on calculating the molarity. Well, right now we know our moles. What we need now is our volume. So if we think back to initially, we had a volume of H+, we had a volume of OH-. The new volume is going to be those added together. So this new volume, 28 milliliters plus 53 milliliters equals 81. Now remember, for concentration, you need liters. So think about how would you go between milliliters and liters? Divide it by 1,000. So you divide 81 by 1,000, that gives you your volume in liters, which means now we have moles, we have liters, and we can use our molarity formula. So molarity is moles over liters. We have moles of OH- divided by liters of solution, and the concentration of our hydroxide ion that is in excess is 0.123 molar. 3 significant figures. That comes from our given information. Now do a double check. Does this make sense? Well, it should make sense because the calculated molarity is less than either of our initial concentrations, so this should work, and this is the correct answer.